Close your eyes. Imagine, for a moment, that you could move as fast as light itself. 299,792 to 458 meters per second. Fast enough to circle the Earth 7 times in a single second. Fast enough to reach the Moon in just over a second. Fast enough to travel from the Sun to Earth in 8 minutes. But here's the strange thing about light speed. You can never actually reach it. Not because your ship isn't fast enough. Not because your engines aren't powerful enough. But because the universe itself won't allow it. And in that impossibility lies one of the most beautiful truths ever discovered. Welcome to the history of the future. Before we explore why we cannot travel at light speed, let us first understand what light actually is. Light is the fastest thing in the universe. Nothing can catch it. Nothing can outrun it. For thousands of years, humans thought light traveled instantaneously, that it simply appeared with no journey in between. But in 1626, a Danish astronomer named Ole Romer proved otherwise. He was studying the moons of Jupiter, and he noticed something strange. When Earth was closest to Jupiter, the moons appeared on schedule. But when Earth was farthest away, they appeared late, 11 minutes late. Romer realized the truth. Light was taking time to cross the distance, 11 minutes to travel across Earth's orbit. From this, he calculated the speed of light, a staggering 225,000 kilometers per second, close to the true value, but still impossibly fast. For 2 centuries, scientists refined this measurement. In 1849, Hippolyte Fizeau sent beams of light through a rotating toothed wheel. By measuring how much the wheel had turned while the light traveled to a mirror and back, he calculated the speed with remarkable precision. In 1862, Léon Foucault improved the method further, using rotating mirrors. The speed of light, 298,000 kilometers per second. We were getting closer, but no one suspected the deeper truth. That this number, this specific speed, was not just a measurement. It was a fundamental limit woven into the fabric of reality itself. In 1905, a young patent clerk named Albert Einstein published a paper that would change everything. He wasn't in a university. He wasn't part of the scientific establishment. He was simply thinking. And what he thought about was light. Specifically, he wondered, what would happen if you could chase a beam of light? What would you see? Classical physics said you should see the light waves frozen around you like a photograph. But Einstein realized something profound. Light doesn't work that way. No matter how fast you travel, no matter how powerful your engines, light always moves away from you at exactly the same speed. 299, 792, 458 meters per second. Always. This isn't a limitation of your ship. It's a fundamental property of reality itself. From this simple observation, that the speed of light is constant for all observers, Einstein constructed something extraordinary, the theory of special relativity. But before we explore time dilation, we must understand another consequence: length contraction. As you move faster, space itself shrinks in your direction of motion. At 90% of light speed, a meter stick pointing forward becomes 44 centimeters long. At 99%, it shrinks to 14 centimeters. At 99.9%, just 4.5 centimeters. The universe doesn't just warp time, it warps space as well. To protect light speed, everything else must become flexible. Time stretches, space compresses. The faster you go, the more the universe reshapes itself around you. And with this reshaping comes the most famous consequence of relativity: time dilation. As you approach the speed of light, time itself begins to slow down for you. Not as an illusion, not as a trick, but as a real measurable effect. Imagine twins. One stays on Earth, one boards a spaceship and travels at 99% of light speed to a distant star and back. For the traveling twin, the journey takes 10 years. But when she returns to Earth, her sister has aged 50 years. This is called the twin paradox. But it is not truly a paradox. The traveling twin has experienced less time because she moved through space more quickly. The earthbound twin, stationary in space, has moved through time more quickly. Space and time are not separate. They are one fabric, space-time. And the more you move through one, the less you move through the other. This isn't a thought experiment. We've measured it. In 1971, physicists flew atomic clocks around the world on commercial airplanes. When they returned and compared them to clocks that stayed on the ground, the flying clocks had lost 59 nanoseconds, exactly as Einstein predicted. Today, every GPS satellite must account for time dilation. The satellites orbit at 14,000 kilometers per hour. At that speed, their clocks run slower than clocks on Earth. If we didn't correct for this effect, GPS would accumulate errors of 10 kilometers per day. Your phone would tell you to turn left into a building. Time dilation is not theoretical. It is engineering. It is the reason your navigation works. It is woven into the technology of your daily life. But why? Why is there a cosmic speed limit at all? The answer lies in the relationship between energy and mass. As an object moves faster, it gains energy. But in relativity, energy and mass are two forms of the same thing. E equals mc squared. Perhaps the most famous equation in all of physics, energy equals mass times the speed of light squared. This equation tells us that mass is simply concentrated energy. A single gram of matter contains the energy of 21,500 tons of TNT. The atomic bomb that destroyed Hiroshima converted less than 1 gram of mass into energy. This is the power hidden in matter itself. But the equation works both ways. Energy also has mass. The more energy you have, the more massive you become. And the more massive you become, the harder it is to go faster. At 90% of light speed, your mass has already doubled. At 99%, it has increased sevenfold. At 99.9%, it's 22 times your rest mass. To reach light speed itself would require infinite energy. And infinite energy does not exist. The universe, it seems, has placed a door at the end of the corridor, a door that can be approached, but never opened. But let us step back for a moment and consider what this means for the universe itself. When we look up at the night sky, we see stars, galaxies, the vast expanse of space. But we are not seeing the universe as it is. We are seeing the universe as it was. The light from the nearest star, Proxima Centauri, left 4 years ago. The light from the Andromeda Galaxy left 2.5 million years ago, when our ancestors were first learning to use stone tools. The light from the most distant galaxies left 13 billion years ago, when the universe was young. Every glance at the sky is a journey through time. And this is because of light speed, because light takes time to travel. The finite speed of light is not just a limitation, it is a time machine. It allows us to see the past, to witness the history of the cosmos, to observe the birth and death of stars, to peer back to the beginning of everything. Without this delay, without this travel time, the night sky would be a snapshot of the present, and we would be blind to the story of the universe. But humans are clever, and we don't like closed doors. So we began to look for loopholes, ways to travel vast distances without actually moving faster than light. One idea came from Einstein himself, working with Nathan Rosen in 1935. They discovered that the mathematics of general relativity allowed for something extraordinary, a bridge through space-time, a shortcut. We call them wormholes, Einstein-Rosen bridges. Imagine the universe as a sheet of paper. You want to get from one side to the other. You could walk across the surface, or you could fold the paper and punch a hole through it. A wormhole is that hole. 2 points in space-time connected. No faster than light travel required. Just a different geometry of space itself. But what would a wormhole actually be like? The mathematics describes 2 mouths. Each mouth is a sphere, a kind of doorway. Pass through one, and you emerge from the other, instantaneously, no matter how far apart they are. One mouth could be in orbit around Earth. The other could be orbiting Proxima Centauri, 4.2 light years away. A journey that would take 4.2 years at light speed, or generations at slower speeds, reduced to a single step. But there is a catch, a big one. The natural wormholes that Einstein and Rosen described are unstable. They would collapse faster than anything could pass through, faster than light itself could cross. To hold a wormhole open, to make it traversable, would require something extraordinary, something we have never found: exotic matter. Another idea came much later in 1994. A physicist named Miguel Alcubierre realized that Einstein's equations allowed for something even stranger: a warp drive. Not the kind from Star Trek exactly, but something that would have the same effect. Here's how it would work. Instead of moving your ship through space, you would compress the space in front of you and expand the space behind you. Your ship would sit in a bubble of flat space-time, perfectly still, but the space itself would move, carrying you along. You could travel from Earth to Alpha Centauri, 4.3 light years away, in weeks, not years, and you would never exceed light speed, because it's not you moving, it's the universe rearranging itself around you. There's a problem, of course. Both wormholes and warp drives require something we've never found, something called exotic matter, matter with negative energy density, matter that, in some sense, weighs less than nothing. This sounds like science fiction, but it is rooted in quantum mechanics. In the vacuum of empty space, particles constantly appear and disappear. Virtual particles, borrowing energy from nothing, existing for fleeting moments, then vanishing. This quantum foam, this bubbling of space-time, creates negative energy. We have measured it. in the Casimir effect. Two metal plates, placed extremely close together in a vacuum, experience a tiny attractive force because there is less quantum foam between them than outside, less energy, negative pressure. Exotic matter is real, but the amounts are tiny. To hold open a wormhole large enough for a human would require the mass of Jupiter in exotic matter. To create an Alcubierre warp bubble would require similar impossible amounts. We don't know if such quantities can exist. The laws of physics may forbid it, or perhaps we simply haven't discovered the right method yet. Perhaps there are ways to amplify negative energy, ways to concentrate it, technologies we cannot yet imagine. Or perhaps these ideas will remain forever in the realm of dreams. Beautiful mathematics, impossible engineering. But here's what I find most beautiful about all of this. The universe has a speed limit, and that limitation has forced us to think more deeply, to be more creative, to look for solutions we might never have considered. The impossibility of light-speed travel hasn't stopped us. It has inspired us. Every day, scientists probe the edges of what's possible. They ask, what if? What if we could? What would we see? Where would we go? Imagine, just for a moment, that you could see the universe as light sees it, at light speed. Time stops. A photon born in the heart of a star billions of years ago experiences no time at all on its journey to your eye. From the photon's perspective, it is created and absorbed in the same instant. It exists in an eternal now. No past, no future, just is. This is perhaps the strangest truth about light speed. Not that it is fast, but that it represents a boundary, a horizon beyond which our concepts of time and space break down. At light speed, distance becomes meaningless. The photon traveling from a galaxy 13 billion light-years away experiences no journey at all, no passage of time, no distance crossed. From its perspective, emission and absorption are simultaneous. The beginning and end of its existence occur at the same moment. This is why light speed is the cosmic limit. Not because the universe is stingy, but because beyond this speed, causality itself would break down. Cause and effect would lose their meaning. Time would run backwards for some observers. The universe protects this boundary, to protect the order of reality itself. And yet, there is something familiar about this. Something that resonates with our own experience. Have you ever been in a dream where you traveled vast distances instantaneously, where you moved from one place to another without the journey in between? Our minds know this mode of travel, this collapse of space and time. In dreams, we are not bound by light speed, not bound by distance. We simply arrive. And perhaps this is why the idea of faster-than-light travel captivates us so. It speaks to something deep in our consciousness, a memory of a freedom we once had. Before we became creatures of space and time, before we learned that you cannot be in two places at once, that you must travel to arrive, that time only moves forward. We are creatures of time. We remember yesterday. We anticipate tomorrow. But light knows only the present. And perhaps in our dreams of light speed travel, We are really dreaming of that freedom, that eternal now, that place beyond time, where all moments exist together, where distance is just a memory, where the universe is one. Sleep well, traveler. The stars will wait. They have all the time in the world. And so, do you.